Hello. Uh, Today we'll start the quantum optics and उसके अंदर क्वांटाइजेशन शुरू करेंगे. Quantization means the idea that idea comes from some physical quantity don't vary continuously. That come only specific discrete manner. Okay, that is the meanings of quantization. Oh, just right here for discrete case. Then in quantization, we know quantization of light, quantization of energy. So, what is quantization of light? Quantization light means where light treated as a mode of discrete packet of energy, where lights are coming as the tiny packets of wave form of energy. Okay, which is not a continuous. So, quantization light quantization is light treated as made of discrete packet discrete packets of energy, not a continuous wave. In class here we just study about the quantization phenomenon. Quantization means it represent discrete case. In case of light, this is applied on the discrete packets of energy. Okay, so we just write if energy of one photon, which is E photon, is equal to h nu, which is hc by lambda. This is the quantization of energy. This is the quantization constant, which is the Planck constant, whose value is h is equal to 6.626 into 10 to the power minus 34 joule second. Here nu is the frequency, and lambda is the wavelength. Uh, in uh, in quantization we study um, photoelectric effect and blackbody radiation and spontaneous emission, but they are classical theory who fails to explain the quantization. Then here in photoelectric effect, we study uh, light um, knocks the electron, which is in terms of h nu, which is the work function, and where here intensity does not matter. Then we study the blackbody radiation. We saw the spectrum and distribution graph. Then spontaneous emission, which is happened in the ledger, where energy is emitted from the higher level to lower level and emitted some photon. That photon of energy. That is the spontaneous emission. Then we start from the classicals. In classicals, we study Lagrangian, Hamiltonian, and Newton. And in classical, we study also Newtonian mechanics, then Lagrangian, classical. Then after that, we explore light matter interaction in semi-classical medium. Then after we come for the quantum mechanics or quantum phenomena. In quantum optics, here we use the classical phenomena. Here we use some classical phenomena. Then some electromagnetic theory on or light matter interaction, classical phenomena, electromagnetic field, and light matter interaction, and some quantum phenomena also. So first, in Newtonian mechanics is applied for only one or two body system. So in many body case, we can't use the Newtonian mechanics. That's why we use the Lagrangian and Hamiltonian dynamics. Lagrangian and Hamiltonian used for the many body system. For many body system, we use Lagrangian and Hamiltonian. Then, oh sorry. Then we represent Lagrangian like L is equal to Q, Lagrangian Q, then Q dot uh, Q dot T. Then Hamiltonian we represent H is equal to H Q P T. Here in Lagrangian we measure the position, then velocity, then time coordinates accordingly. But why classical mechanics for in classical mechanics हम लोग न्यूटनियन मैकेनिक्स की जगह लैग्रेंजियन मैकेनिक्स क्यों यूज किया? क्योंकि मेनी बॉडी प्रॉब्लम सॉल्व करना था, तो इसलिए हम लैग्रेंजियन मैकेनिक्स यूज किए। तो बाकी लैग्रेंजियन के मैकेनिक्स यूज करने के टाइम में हमको क्यों हैमिल्टनियन मैकेनिक्स का जरूरत पड़ा? तो वो भी एक प्रॉब्लम है, क्योंकि कुछ मोशन को डिफाइन करने के लिए लैग्रेंजियन का सही से सही से लैग्रेंजियन डिफाइन नहीं कर पा रहा था, तो इसलिए हम हैमिल्टोनियन का यूज किए। जैसे कि हैमिल्टोनियन में मोमेंटम को सही से डिफाइन कर पा रहे, तो इसमें हम मोशन का कैलकुलेशन सही से कर पा रहे थे, तो इसलिए हमको हैमिल्टोनियन का जरूरत पड़ा। देन हम आएंगे तो जनरलाइज्ड कोऑर्डिनेट के बारे में। जनरलाइज्ड कोऑर्डिनेट में जैसे कि जैसे कोई नॉर्मल कोऑर्डिनेट सिस्टम होता है, एक्स वाई जेड, पी क्यू एक्स क्यू वाई क्यू जेड, these are the generalized coordinate. Simply we take the canonical, here we use the canonical coordinate system. Canonical coordinate system, here we use the position and momentum and time also, like qx, q n px pn or t. This is we taken for the canonical coordinate. Here we use the classical mechanics and electromagnetic theory and light matter interaction and quantum phenomena. We'll see the what will happen in classical mechanics. We will deal with this thing. Then, uh, in Heisenberg, in Heisenberg, sorry, Heisen principle. There then Heisen. Wait. यार हम लोग अभी देखेंगे हाइजन प्रिंसिपल कैसे था। हाइजन प्रिंसिपल इज डील्स विद द इंटरफेरेंस एंड रिफ्लेक्शन which is applied on the wavelets, that state spherical waves act as a secondary wavelets like this. uh, Here we applied for the longitudinal waves. Then after that, hygienes, we use that we study for the light phenomena. That is that study on light phenomena. Then we study again for the polarization, where Maxwell comes to action. Maxwell, he states four equation. that is del dot E is equal to rho by epsilon naught, del dot B is equal to 0, del cross E is equal to minus del B by del T, then del cross B is equal to mu naught epsilon naught del E by del T. So we'll deal with this Maxwell equation in the quantization of radiation or quantization of EMOF. Then next we will go for the how quantum phenomena will become in de Broglie in de Broglie principle. We know light have dual nature, that is light particle and particle. Another is wave. Here wave are coming in tiny small bunch of packet of light are coming with some bunch of wave packets. This is coming in discrete manner. This phenomena is known as the quantization, called the quantization part. This explained by the Planck's, and Planck's described in 1900, and after that 1905 it verified it. He said wave packets are coming discrete manner. So here energy is directly proportional to frequency of the light. Then have some constant, that is Planck constant. He used the Planck constant H. Then we can write E is equal to h nu, which is the energy equation of the quantization of light. Then then we start um, then we start the quantization when part where light matter interaction is happening. Light is the classical wave, classical electromagnetic wave, which is smooth uh, and have some energy. Okay, so the light matter interaction happening in the semi-classical model. Interaction happening interaction happening in the semi-classical model. Here in matter we consider some atoms, objects, anything. Then how it interact with light and give some result we study in the semi-classical model. Then it describes something, describe successfully like all optics experiments, optics experiments such as um, diffraction, interference. This is happening in semi-classical case. Semi क्लासिकल केस में ये डिस्क्राइब इसको सही से डिस्क्राइब कर पाया, जो कि डिफ्रैक्शन और इंटरफेरेंस एंड फ्री प्रोपगेशन ऑफ लाइट. देन और क्या सही से डिस्क्राइब कर पाया, देन ऑब्जर्प्शन सही से डिस्क्राइब कर पाया, देन स्टिमुलेशन एमिशन ऑफ लाइट, stimulated emission of light by matter, uh, then uh, ex, uh, then laser fields, which is based on the stimulation emission. Then uh, it could not describe. Uh, it could not describe. Cannot describe. Cannot describe. क्या describe नहीं कर पाया? Spontaneous emission describe नहीं कर पाया. Spontaneous emission describe नहीं कर पाया. Because of excited atom just scattering alone with no wave, still radiation happening. So this one is not described. That is spontaneous emission. This thing is happening in semi-classical quantization model. Then fully quantized model, in fully quantized model, it describe light phenomenon, which is the quantum. We study the quantum nature of light in empty space. In empty space, how quantum fluctuation happening due to light. So here we study spontaneous. Here we study spontaneous emission. Then for here already this thing is not described properly. So here we study for one photon system. For one photon system, photon is the uh, quantum of light, one unit of light. Then वन फोटन सिस्टम के लिए इसमें स्टडी किया जाएगा. देन एंटेंगलमेंट स्टेट के लिए स्टडी किया जाएगा, जिसमें टू फोटोन साइमल्टेनियसली रोल शो करेंगे. उसमें एंटेंगलमेंट में स्टडी करेंगे, जो 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 कि टू फोटोन सिस्टम के लिए. एंटेंगलमेंट टू फोटोन सिस्टम के लिए. देन स्क्वीज स्टेट. Then we study squeeze state, where make where the noise where the noise in one property very small. This squeeze property used in LIGO detector. LIGO detector is the which work for the detect the gravitational waves. Then squeeze state of light were produced for the first time, allowing one pass to what had been considered a fundamental limit. So this is called the quantum limit. Squeezed light means squeezed light means measurement with measurement with an unpredicted measurement with unprecedented unprecedented quantity. measurement with an unpredicted sensitivity. Sensi- Then next, this is for fully quantized light. Next, here we study quantization of free radiation in one mode. मतलब सिंगल फोटॉन के बारे में पढ़ेंगे. क्वांटाइजेशन ऑफ फ्री रेडिएशन. क्वांटाइजेशन ऑफ फ्री रेडिएशन in one mode. This is applied on the semi-classical model. So here we use the classical Maxwell's equations, and using a method, using the method of canonical quantization. So in this free radiation of one mode, we study the quantization material harmonic oscillator, then single mode of radiation, canonical quantization of a single mode of radiation, observables, and then number states of photon, then vacuum fluctuation. Then here we start from the canonical quantization. Canonical in canonical quantization we know here we we in we use the canonical coordinates where position and based on the position and momentum and time. What is the canonical quantization? That any system of which we have classical description can be quantized, a process known as canonical quantization, which is given by the Dirac. In classical system, the dynamic variables are in classical. Dynamic variables are Q1, Q2 up to Qj, Vi to V1, V2 to Vj. Here we take if we take the time coordinate, or we can write if we write energy of T is equal to Hamiltonian of here we define Hamiltonian. It's used as the energy operator form. We can write in classical notation as E of T is equal to H. Then here Qj of T and Vj of T. Energy of position and linear momentum respectively. Then now we'll write the possible sets of dynamic variable, which is some possible state of dynamic taking the t is equal to t naught, here t naught. If t is in greater than t naught, we'll write v1. If similarly qj v1. We'll write this one. Next, this q, j, and pj is the canonically conjugate variables. That is the canonically conjugate variables. That is the canonically conjugate variables where q, j, and pj, it will, if we will written in the operator form in quantum mechanics, we write qj operator, then pj operator. We know the value, right? I h cut written like x I cap, x cap, and p cap. That value is I h cut. Here, qj represent x, means it represent the position. Pj it represent the p, the means is the momentum. Then that x cap and p cap it's give is not is got. Then next we write uh, if the this is the canonical dynamic system or dynamic variable system, like q1 up to qj, then p1 pj. So we write it qj cap and pj cap, which I is called delta jk, where jk is that represent delta jk is the chronicle delta form. We know accordingly if delta j and k is equal, then its value will 0. If different, that will be written like. Then next quantization, then we'll write the canonical Hamiltonian, then canonical Hamiltonian here. Canonical Hamiltonian, where E energy is equal to E of A is equal to H of E V Q1 Q2 of Qj and P1 P2 of Pj. So we write energy as a Hamiltonian operator. So Ah cap is equal to H Q1 cap Q2 cap of Qj cap, then P1 cap P2 cap Pj cap, which is the this is called the quantum Hamiltonian. This is called the quantum Hamiltonian. This is called the quantum Hamiltonian. Next, then its quantum property will be like we know that S of psi n is equal to En of psi n, which is the, these are the states where H is operates on some space state that is that on the psi n. Here is the energy eigenvalue. This one is the energy eigenvalue. This one is the state which is multiplied with the energy eigenvalue. This is coming from the time independent Schrodinger equation. Comes from the time independent Schrodinger equation. So which is the derived from the time independent Schrodinger wave equation, which is the we know which is we know that is I h got del by del t of psi of r t, then minus h got square by 2m of del square of v of r t, then psi of r t. Here we taken in the form of wave, that is psi of r t of psi of r, and some time terms t, where the psi of t is equal is it um, time evolution operator, that it sorry, that is e to the power minus e t of h got. If we put this value, that is minus h got square by 2m del square plus v of r, then psi of r, then e of psi r, then we get like this in operator form. If you take the Hamiltonian operator h, then if that is the psi r, then e of psi r we getting. So here we get this thing. Next, we can write in this kind of form I h got by d I h got of d dt of psi, which is equal to h of psi, which is the energy operator in terms of energy operator, which is called the quantized. This is called the quantized Hamiltonian. This is describe a state of system at time t, that describe a state of system of at time t. This is given the idea about the Schrodinger equation. This is the this is the Schrodinger equation. So here we can write, if the classical Hamiltonian energy system is equal to E h of, so here we write the energy in the classical Hamiltonian system is equal to h of q1 q1 p1, then q of j and p of j, like this. Then we calculate from this energy equation, that is dpj by dt is equal to dh by dpj, then dpj by dt is equal to minus of del s by del qj. And then if we take a system like it is u of x system and here x, this is the core continuous core. Then we use the hypothesis that that is the canonical conjugate variable uh, are the position and the momentum form. If we take the q is x and the p is the m dx by dt, then we write the energy that is u is equal to u of x and plus p square by 2m, where we can write energy in the form of the Hamiltonian. Then H is equal to U of Q plus P square by 2m. From this above, we just write it is dx by dt is equal to del H by del P, and del x by del dx by dt is equal to del H by del P, where value will be here 2p by 2m, which is the p by m. Similarly, if we calculate dp by dt, here energy and Hamiltonian we know in the form of the time term. So if you take the derivative with respect to the time, and the dp by dt, will be minus dh by dt from this. Then what will be happen? Then answer will be minus del u by del x, which gives the idea about the force. That is the form of the Newton in the Newtonian equation. In classical Hamiltonian, we know that is H is equal to p square by 2m, some v, that is u of x in terms of u of x, that potential energy. In the quantum Hamiltonian, we write H in the operator formula regime p operator square by 2m plus u of x cap. Then here for relation between the position and the momentum, that is x cap and p cap I h cut, which is this operator form of commutation relation is gives idea about the Heisenberg uncertainty principle. It says we can define at a time position and momentum of the particles, so it can't be zero or satisfied the commutation relation. So this is the case. Then next for the Schrodinger equation, wave function representation is the for the Schrodinger equation, wave function representation is that is peak of cap is equal to I minus I h got y del by del x. We know the momentum operator. So here we can write in the Schrodinger equation form, that is I h got d by dt psi of xt, which is the Hamiltonian operator or energy operator. So here u of x, which is the potential energy, minus h square by 2m d square by dx square psi of earth. xt. These are the states. This is comes from the behavior of a particle in a potential well on event to calculate the energy levels of the hydrogen atoms. From this we calculate for the hydrogen atoms also. Then canonical variables are the position and velocity. So in terms of position and velocity, we take q is equal to x and p is equal to v. So we write h is equal to e, which is half mv square plus u of x. So we write dq by dt, which will give del h by del p. Then del q by del p, which will be give del h by del v. Then here del h by del v will be m v. Then del p by del t will give del p by del t will give, we take from here also. Okay, we take calculate from here this thing. Del p by del t will be del p by del t will be minus del h by del q. Then del v by del t will be minus del h by del q. So the answer is minus del h by del q. Uh, Here q means position, which is the minus del u by del x. So here it gives the idea the x and v are not canonically conjugate variables. So here it gives the idea about the it's not a canonically conjugate variables. So x and v canonically conjugate variables. So it's finished. Next, next we'll next we'll go for the material harmonic oscillator. We just start little bit. After that, next time we'll do others. Material. In classical mechanics, we just study the some many body problems in the Lagrangian and Hamiltonian dynamics. After that, in quantum, when we start studying the quantum, first light properties comes in the black body radiation, where a black body is absorb the lights. In ideal black body absorbs the lights, so and emits the lights. So this phenomena when blackboard radiation is started, then there some um, result will come. A ideal black body is completely absorbed and radiate that from is come. if a black body is there, then the black body is absorbs some light and so, emits something. So there is the spectrum of the graph like this is come. Then there relay genes is come for the clarification of this thing, but relay genes fails to explain in the high frequency range where the light frequencies varies at the infinity or in high frequency the graph will be vary. So relay genes is fair. Then after that uh, then after that the Planck radiation of light is come. Then he described the quantum nature of light. Who was in classical case relay genes is explained in the form of simple harmonic oscillator in classical harmonic oscillator. But in quantum Planck is come and explain about the quantum harmonic oscillator, where the energy is the E is equal to, that is nx plus sorry n plus half h got omega. So that satisfy for the low frequency range, that satisfy for the low and high frequency ranges, where equation is uh, E u nu is equal to 8 pi h nu square divided by c square of e h nu by kt minus 1, like this. So this one is satisfied for the low frequency range and the high frequency range. Then here we start in metal harmonic oscillator, we study for this quantum case. Now we'll apply for the canonical quantization. Here we apply the canonical quantization case in the material harmonic oscillator. The main reason of the formation will develop because of in the quantum optics we study study and see how quantized radiations behaves in the quantum harmonic oscillators. Yes. Here we use some method that was the derived by the Dirac. So here, classical harmonic oscillator, that is material particle of mass m, which can be moved in the x-axis and is attracted around x is equal to 0 by the elastic force proportional to the distance. That is here it will be oscillate. Here x is equal to 0. That one is the x-axis. It is the potential energy. So we write that is u of x is equal to half m omega square x square, which is the force derived from the potential for a potential. Then h, we know h is equal to h square p square by 2m plus uf for x, which is written p square by 2m plus half m omega square x square. If we calculate, that is dx by dt according to the canonical quantization, dx by dt, we calculate dx by dt. Here dx by dt will be del h by del p, which whose value will be p by m. Similarly, we use something like dp by dt, dp by dt, and where d value is minus del h by del x, which is the minus m omega square x. If we calculate d square by x by dt square, which is the minus omega square x. If we take x is equal to a cos omega t plus phi, then p, if we take p is equal to minus m omega a sin omega t plus phi, where we take x equal to x naught and t is equal to t naught, and p is equal to p naught and t is equal to t naught. This momentum is proportional to the derivative of x and oscillate in quadrature. This momentum oscillates in quadrature. Then here we'll study that that is some x value and y value and x value and p value. We check that is x is equal to a cos omega t plus phi. Then p, no, in this ax we can write in the exponential form, that is amplitude a e to the power iota minus iota omega t, which changes that happening changes pi. We conclude the some complex conjugate. A amplitude where a is equal to e to the power minus iota phi a by 2. Similarly, similarly we take for the momentum minus omega a sin omega t plus phi, where we take p is p naught and t is equal to t naught. Then we write in the exponential from minus iota omega m a e to the power minus e to the power minus e to the power iota minus iota t minus iota omega t plus 1. Next, we study the geometrical harmonic oscillator using the same canonical quantization process. Here, uh, if needed, next I will show the calculation of this quantization of the quantization form, that is dx by dt and del x by del p. So there we calculate these things for the position and the momentum we calculate, and we represent in the form of the exponential. We represent like this: I omega m a e to the power minus omega t For the phase case, we take some additional constant, that is canonical sorry, complex conjugate terms. Then here here it comes some amplitude, which is the in the form of e to the power minus a phi by pi a by 2. Next, here use geometrical harmonic oscillator. Geometrical harmonic oscillator. Sorry, diagram is not good. This should be symmetric. Okay. Then this one is u of x. Then this x. Here some particle will be oscillate like this. This is the different energy levels, different state of levels. Here I take Hamiltonian, that is p square by 2m plus v of x. We write in the operator form p square by m. Then that is p square by 2m plus half m omega square x square. We know the canonical conjugate, canonical commutation relation of x and p is equal to iota h squared. So I replace x cap in terms of x and p cap, p operator in terms of the minus iota h squared by del x. So we know the Schrodinger equation. Schrodinger equation we know, that is minus h squared square by 2m d square by dx square plus half m omega square, then phi of x, then e of phi of x, which is the time independent Schrodinger equation. Here we calculate the energy, which is the En is equal to n plus half h cut omega, where n value will be 0 to 1, 2, 3 up to n. So we know the finding the probability from minus infinity to infinity. Um, at that wave, at that wave function, finding the probability of the particle at that wave function or at that wave, we know that is one. पॉसिबिलिटी वन ही है, तो कैसे भी एक ही वेव में कहीं पे भी प्रोबेबिलिटी कैलकुलेट करने के लिए, टोटल वेव में प्रोबेबिलिटी कैलकुलेट करने के लिए प्रोबेबिलिटी ऑफ सम इज वन. सो minus infinity to infinity mod of psi of x squared dx, which will be 1. So where psi is the wave function which is the integrable over the space, then here we calculate, here one finds a discrete state of solution. We'll find a discrete state of solution, and then parameterized by the non-negative integers. So if we write the wave equation like psi of n is equal to exponential of minus half omega m x square by 2 h cut x 2 h cut h1 of x. Here hn of x is the Hermite polynomial. We know h naught of x is equal to some value that is 1. H of 1 of x is equal to 2x, and h2 of x is equal to 4x square plus 2, something like this. Uh, we know this thing is the Hermite polynomial. This is taken for the harmonic oscillator wave function, harmonic oscillator wave function. Then finding the particle at the wave, then that is the one, that is the probability we take. That wave associated with the product of Gaussian that ensure the asymptotic null value, which is the Gaussian wave function. This one is the harmonic oscillator wave function or Gaussian wave function. We got some Gaussian wave in that ground state, yeah, something. So that is the wave function of that. That is the Gaussian wave function. That one is the Gaussian wave function. This is the Hermite polynomial. Hermite polynomial with degree n. Then next presentation I will show the quantum harmonic oscillator in direct formulation. Then I will show the quantization free radiation in the one mode of radiation also. Uh, next next I will show the EM mode radiation, free radiation also. This one is the one video, one presentation for my uh, quantization of light and quantization part. Then another part I'll show next presentation or next week also.